everyone, in this video we're going to take a look at how equilibrium is related to spontaneity. To see this connection, let's go all the way back to our definition for spontaneity, which says that a spontaneous reaction occurs on its own without any outside intervention, but in the direction of equilibrium. And if you think about equilibrium as the stopping point for a chemical reaction, meaning a reaction happens until it reaches equilibrium, it makes sense that this is what spontaneous should mean. We're really just saying that the reaction happens until it stops at the point of equilibrium. Now, to see exactly how free energy and equilibrium are connected, we'll take a look at a series of connected ideas, starting with a negative delta G value. So by now we should be pretty comfortable realizing that a negative delta G tells us that free energy is released, which tells us that the reaction is spontaneous as it's written. So if you think about this idea of spontaneous, it's just telling us that the reaction happens. And if the reaction happens, that's like another way to say that the reaction will make products. And in the world of equilibrium, a reaction that makes products is also a reaction that is called product favored. That means at the point of equilibrium, there are more products than reactants, which is essentially what we're saying for spontaneous reactions. And if it's product favored, remembering that our K value, the equilibrium constant, is a ratio of products to reactants, the top of which we know will be larger than the bottom for a spontaneous product favored reaction, we can expect a spontaneous reaction to have a K value greater than 1. We'll see this same series of ideas starting with a positive delta G. Positive delta G, that's a reaction that's not spontaneous as it's written. That's the same thing as saying that it doesn't happen or doesn't make any products. And in the world of equilibrium, not making products is essentially being reactant favored. And the K value for a reactant-favored process where the denominator is larger, we can expect it to be less than 1. Now, this relationship is also scalable, meaning the more negative the delta G is, the more products will be present at equilibrium. You could expect a larger K value, or the more positive the delta G is, the more reactant-favored that reaction will be, you could expect a smaller K value. These are our key ideas for this video, so make sure you take a moment, pause, and write them down. Lastly, we need to talk about the mathematical relationship that exists between spontaneity and equilibrium. You can find this equation on the thermochemistry section of your AP chemistry equation sheet, right beneath delta H minus T delta S. The equation is delta G equals negative RT ln K, R being our gas constant, of which we have many values to choose from. For this, we're going to use 8.314 joules per mole Kelvin. The T value, of course, is temperature in Kelvin, and capital K, of course, our equilibrium constant. Let's use this example question to apply this mathematical relationship. Feel free to pause the video and try it yourself if you'd like, before hitting play and taking a look at my solutions. So this question asks for the equilibrium constant, that's capital K, for this reaction at 25 degrees Celsius. This would be easy if I was told the delta G for the reaction, which I'm not. Instead, I'm given this series of free energies of formation. Now I can use those to calculate the delta G for the reaction by taking the sum of those values of the products minus the sum of those values of the reactants, much like we would do with enthalpies of formation. Plugging everything in, I've got my product value minus my reactant values, which you'll notice are just 0 because they're elements in their standard state. I come up with a delta G of negative 16.37 kilojoules per mole. Now right away I notice this is negative, meaning the reaction is spontaneous. So I'm expecting to make more products than reactants, or a product favored reaction, in a K value larger than 1. Let's plug in that delta G to my new equation and see if that's true. First thing I'll need is our new equation, negative RT ln K. Let's plug in the delta G over here. Notice I've changed it to joules, 16,370. My R value of 8.314, 25 degrees Celsius in Kelvin is 298 K. Simplifying all those numbers to 6.607 equals natural log of K. Finally getting rid of that natural log and ending up with an equilibrium constant of 735, which is much larger than 1 as we expected for this spontaneous product-favored reaction. And that's it for this video on equilibrium and spontaneity. Thanks for watching.